Okay, so this is an introduction to Melinda Green's 2x2x2 Rubik's Cube type puzzle. It is a 4D analog of a regular 2x2 Rubik's Cube, whereas a 2x2 Rubik's Cube has 6 faces, each being squares that turn independently of each other. This 4-dimensional puzzle has 8 faces, and each of those faces is a cube, which turns independently from each other. Each piece, in addition, this is one piece, has 4 stickers on it. The stickers each are cubes, which are squished down to fit into 3 dimensions, which is why they look like these tetrahedral shapes. There are 4 stickers, unlike the 3 stickers on a 3-dimensional 2x2. This puzzle is put together using 384 magnets arranged in such a way that it can move in all possible ways that a real 4-dimensional Rubik's puzzle would be able to. What these magnets do, though, it is not restricted to those moves. Because of the magnets, it can move in all sorts of ways that would not be allowed in a 4-dimensional puzzle. So, because of that, we have to restrict what moves we do in order to keep it within the restrictions of being a strictly 4-dimensional puzzle. To do that, there's six canonical moves, not 4, 6 canonical moves that we use to manipulate the puzzle when solving it. 2 of these moves are rotations of the puzzle in the 4D space, whereas this is a rotation in the 3D space. Like doing this, a rotation in the 4D space requires movements of the pieces but does not change the physical state of the puzzle. We can roll 2 halves together, putting adjacent squares together, and that is a rotation of the puzzle and doesn't change the solved state, which means that all the sides are, all 8 faces, the cubes, are completely the same color. We can see that this inside, they're all touching. All the orange pieces are touching. If we roll it onto this one, now all the white pieces are touching on the inside. And then we can roll it so that any of the 6 sides of each half are touching. That's only 6 of the faces. The other 2 encompass each of the half of the puzzle. So these pink stickers are pseudo-touching, and they're solved because they're all on this same half of the puzzle. Same with these purples. That's another face. That's one type of rotation. There's another type of rotation that rolls it into the 4D space, so to say. That requires a few moves to execute, and these must all be done together to be canonical. So this is called a gyro move, and it rolls it so that the pair of axes facing you, in this case the orange-red pair, is switched with the pair of axes that is pseudo-touching the pink and purple. To execute the gyro move, we take the top slice of the puzzle, place it on the bottom, separate the puzzle, push it backwards like so, put it together, and flip it down in front. Then we reorient it like so that you can see there's those 2. When solved puzzle, it would be like that. Pull it apart like that, this time not separating it, pushing it, folding it in half, and doing that one last time. And now we see that the pink and purple are right there, and the red and orange are on the outsides. You can do that again, top to bottom, outsides apart, and then pushed back together, and then separated outwards, pushed together in half, separated, and folded in half. And now we're back to where the rotation of where we originally were. And each gyro move, where the red stickers were completely on the outside, and this one are identical states of the puzzle, just rotated differently in the 4D space. The other four kinds of moves are movement of the axes. There's 4 axes because there's 8 faces. The first axis I'll talk about is the outside axis that's pseudo-touching. That would be the pink and purple axis in this case. To move across that, we can just separate the two halves of the puzzle and then rotate these in any which way that we want to. That's because by rotating them in any which way that we want to, we're just doing compound moves of it along this part of the cube, that part of the cube, and then this way. So we can just take it apart, put it back together however we want to. That's one pair of axes. The next pair of axes is on the center. We've got this yellow on the inside, which is opposite the white, which is on the outside. To move this inside pair of axes, it's slightly restricted. It can't move through all the 4D spaces that would be possible on a 4D cube, but that's allowable with the gyro move. While just in this state, we can do 90-degree rotations of that inside face along this rotation. So to do that, we can move these inside 2 slices, and that'll rotate this yellow face increments of 90 degrees, like so. The next 2 axes are very similar to each other. They're going to be the axes on the outside of the cube. So the green and blue, and then the red and orange. To move those 2, we are even more restricted than the inside, and they're only allowed 180-degree rotations in this direction. So to do that, we can take the cube apart in half, flip it over, and put it back together. We can do that with both the front, the back, and both sides. So that's the 4 different kinds of moves that we can do. Next, I'm going to talk about scrambling the cube. It's a little bit harder to scramble this cube than to scramble a regular 2x2. On a 2x2, you can access all the moves that change stickers around to all the faces. But if you've noticed, all the moves that I've described so far do not exchange any of the stickers with this outside axis, the pink and the purple. So no matter what I do, just moving along random faces, doing inside moves and side moves, Z moves, no matter what I do, I'm never going to exchange any stickers with the outside axis. So to do this, we could do a gyro move, but that's slightly time consuming. So Melinda Green came up with a way that preserves the permutation of the puzzle while violating some of the canonical moves. But it's okay because the puzzle is still in a solvable state and we're only scrambling it. To do that, we can just take the top to the bottom, like in a gyro move, and then just replace the 2 sides, like so. And that keeps the puzzle in a solvable state and does a few moves, but essentially just takes the outside stickers to this inside front. It doesn't keep the puzzle in the same state, and those aren't canonical moves, but we can use those to scramble. So we can do that interchanged with some of the random movements of the other 3 axes. And by doing that, we can get to a scrambled state of the puzzle. Should be sufficiently scrambled enough. This next section, I'm going to be talking about ways to manipulate the puzzle in easy and reliable ways. This first half of talking about this, I'm going to talk about when we don't care much about the outside stickers. To do that, let's say we want to solve this purple group of 4 right there and get 4 purple pieces right there together. What we can do is we can bring this over to the bottom, and now we see we've got a bar here. while dealing with the whole state of the puzzle, working with bars makes it the easiest to work with. So we've got this purple bar right here, which means that we can use this move and this side move without disrupting this bar at all. What we can do is we can say, okay, we've got this attached purple sticker right here. If we were to first move it to the top, we see that it goes right there. We can then move any of the other purple stickers on this face around so that it matches up with it. We already had that, so by doing that, it pairs these two up right here. Now we still have this slice free. If we were to do it again, it would unpair them. What we can do is then just twist this top like so that it's completely on the half that we would rotate, and now bring that down to the bottom, and that pairs those four up into a face. That's an easy way to make one face, but to do much more than that takes a little bit more tricks. After that, let's say we want to make let's go with blue. Nope, can't access that because it's attached to the purple right there. Let's say we want to make a green face. Why not? It sounds fun. Let's do green. So it's already on the half of the puzzle that we have free. So let's move. We know that it's going to end up right there if we move it back up. So we move it to the bottom, which leaves this part of the puzzle free. We can then move this green sticker right next to where it would go, bring it back up, and that then creates a bar which we can bring to the bottom. Now, if we look for any green stickers, there's one right here. We can actually, that's not very helpful to us, so we can actually bring the puzzle back, bring this bar back to the top, and then rearrange how we bring it to the bottom. Let's say, let's put it on the side and now bring it to the bottom. And that leaves us with a green sticker right there on this face. We want to look for where the green sticker on this four pieces are, besides these two. So it's right there. So if we were to bring that green sticker to the top, it would end up right there. So we can manipulate this one cube to put the green sticker right next to where it would be. So it's going to end up right here. So we'll put this green sticker right there, place it back together, move this to the top, and that pairs these two. Now we can move this to the bottom. We can move this back up so that when we move this, that we've all paired them into a face. And those are easy ways to using the full set of the puzzle to move around pieces. And none of those moves will take any of the outside stickers to the inside, but they might mess up where the outside stickers are. For this next part of demonstrating how to manipulate the puzzle, I'm going to start off with a solved puzzle. You might have noticed that if we look at just this one half of the cube, the sticker scheme lines up exactly, minus the purple corners, with that of a regular 2x2. And if we just do a little finagling on a different 2x2, we can get the bottom to have the exact same sticker scheme as well. So that brings the question, is it possible to manipulate each half of the puzzle exactly like we would a 2x2? And the answer is yes, we are able to do that by using a so-called buffer piece on one of the layers. Let's say we wanted to perform an R move on this half of the puzzle. Assuming, let's say if this is a 2x2, we wanted to perform an R move on this. On this cube, an R move would look just like that, a clockwise rotation of the right side. To do that on here, using this as a buffer piece, we can use that movement of the inside layer to make that R move. We can put this right side face down onto the inside. So now when we make any movement of the inside layer, it's manipulating the right side of the puzzle. A quirk, because the right side's facing down, if we want to make a clockwise move, we actually have to move this inside layer counterclockwise. So now we can put it back to its original, this top half to its original orientation. Now if we take a look at it, compared to this puzzle, which we did in our move on, they're in the same state. The inside stickers are. And this bottom puzzle has only been moved, but it's only one move away from being solved. And no matter how many different face moves we do, this will always be one move away from solved, because we're only ever moving that half of the cube. So we can use this in conjunction to perform any number of algorithms that we know on the 2x2 on each half of the puzzle. I'll demonstrate with an example of the soon algorithm. So soon is used in advanced 3x3 solving, in beginners 3x3 solving, and in the Ortega method on the 2x2. So most people are probably familiar with this, even if they don't know the name of it. It goes like R, U, R prime, U, R, U2, R prime. And so if we are able to execute that algorithm on just half of this, we should be able to get one half of the puzzle to look exactly like this. So that algorithm again, so then we can do the algorithm here. We want to do an R move first. So we can put the right face down, move it counterclockwise, because an R move is clockwise. Put it back. We want to do a top move now. Let's put the U up face down. We're going to do clockwise, so we're going to move this inside counterclockwise. Put it back. Next was R prime. We're going to put the right side down. Move this inside now clockwise, because we wanted to do a counterclockwise move of the right. Put it back. We wanted to do U again. Let's put the top down. Move the inside face. Put it back. We wanted to do R again. So let's do right side down, counterclockwise. Put it back. Next we wanted to do U2. Put that down. 1, 2, 1, 2. Put it back. And lastly we wanted to do R prime. Put the right side down, move it clockwise. So now if we take a look at this half of the puzzle, we just did all the moves of the soon. And if we look at the stickers, white, orange, green, red, white, orange, green, red, white, blue, orange, orange, yellow, blue, green, green, and so on. And all of the stickers match up on this half of the puzzle and a 2x2. Now if we take a look at the bottom half of the puzzle with this buffer layer, nothing happened to the puzzle because this algorithm has a net rotation of modulo 4 moves, meaning that we did 4 quarter turns of this buffer piece, so nothing got changed in it. And with that, we are able to perform any algorithm we want to on each half of the puzzle at any point in time in the solve. It's one of the most useful pieces of information to solving the cube tesseract thing. Thanks for watching. I will also be uploading a video on a tutorial and beginner's method for this Melinda Green's 2x2x2x2, as well as eventually a tutorial and method for my more advanced speed solving method for Melinda's 2x2x2x2. Thanks.